Hi! In this video I will introduce to you the technique of so-called partial fraction decomposition. It's a way to split up a rational function into simple terms. Rational function? Here's one. And here you see some more. Okay. A rational function is the quotient of two simple functions, namely two polynomial functions. Just like a rational number is the quotient of two simple numbers, namely integers. Partial fraction decomposition can, for instance, be used to find integrals of rational functions. For the one on the slide, you really don't need it. The answer is just the natural log of x plus 3. And the second integral is also not really a brain teaser, is it? But what about the third? In fact, partial fraction decomposition means breaking up a rational function into terms like the functions in the first two integrals. Let's now focus on the function in the last integral. Let me just give you its decomposition straight away. Note that the terms on the right are indeed easy to integrate. The identity is easily checked. Adding rational functions is just like adding rational numbers. You start by giving them a common denominator and then add the numerators. So, starting from the terms on the right hand side, by convenient multiplications, we make the denominators equal, then add two fractions and simplify. Mission accomplished. As often, checking whether a solution solves a problem is easy. The hard part is finding the solution. Let's go back to example 1, 1 over x squared minus 1, and for the moment forget about the decomposition. The crucial step is to factorize the denominator. In fact, that's the hardest part. Here it is quite easy. X squared minus 1 equals x minus 1 times x plus 1. So we might try to write the function into the form a over x minus 1 plus b over x plus 1. After all, adding these gives us a fraction with the correct denominator. By the common denominator trick, the terms can be added, and it remains to find the values of a and b for which the last numerator is equal to the original numerator, which is 1. Comparing these numerators, we see that a times x plus 1 plus b times x minus 1, which is equal to a plus b times x plus a minus b, should be equal to 1 for all x. This leads to a set of two equations for a and b, two linear equations with, in this case, a unique solution, namely a is equal to a half and b is equal to minus a half. So we end up with the partial fraction decomposition a half times 1 over x minus 1 minus a half times 1 over x plus 1 indeed. Right. As I mentioned, finding a factorization of the denominator in linear and sometimes also quadratic factors is in fact the hardest part. For an arbitrary polynomial function, there's not a general technique to do this. The reason is that there is not a general method to find the zeros of a polynomial function. Once the factorization is found, it still needs some attention to break up the given rational function into convenient simpler terms. There are specific rules for this, but here I will certainly not go into all the technical details. Instead, I will just look at one other example to show one of the complications that may arise. Namely, I will discuss the following slightly more involved rational function. What would be the decomposition for the rational function you see here? Note that the denominator is already factorized and that the quadratic factor x squared plus 1 cannot be factorized further. For this function, a first thought might be to split it into the terms a over x plus 1 and b over x squared plus 1. As you add them, you get at least a rational function with a good denominator, x plus 1 times x squared plus 1. However, if we do so and we compare the numerators, we see that we have to make a times x squared plus 1 plus b times x plus 1 equal to 1. So equality must hold between two second-order polynomials. Comparing the coefficients of the terms x squared and x and the constant term, we get three linear equations for the two unknown parameters a and b. In general, that's too many equations, and so it is here. The set of equations for a and b is inconsistent, so this decomposition does not work. Then what? I promise you there is a general rule for a good decomposition involving just the right amount of parameters. To round up this first introduction, I will just tell you what the escape route is for the function at hand. Here you see a decomposition that's going to work. A third parameter is introduced in a sort of independent way, and from this appropriate start the rest goes smoothly. The two fractions on the right I added as before, and comparing the numerators again leads to a system of three equations, but now we have three parameters. As before, these equations follow from the comparison of two second-order polynomials. Let's make some room and focus on the terms that are framed red. When we compare the coefficients of x squared and x and the constant term, we find three equations for the three parameters a, b and c, which now fortunately is a consistent system with a unique solution. You can use your favorite method to solve it and will find that the solution becomes a and c are equal to a half and b must be equal to minus a half. Plugging these values into the top equation, we get our partial fraction decomposition of the rational function 1 over x plus 1 times x squared plus 1. And now, time's up. Thank you for your attention. Goodbye.